Hi, everybody. It's Professor Mitchell. So I thought I'd make this video for the end of Chapter 8. We came very close to finishing Chapter 8 in class. We didn't quite make it, so making this so that we wrap up Chapter 8. So we've just been talking about confidence intervals for population proportion. So this next part has to do with determining the sample size needed if you want your confidence interval to have a given margin of error. All right, and the example I keep coming back to is you're doing a poll for an upcoming election, and let's say you want to know how many people do you need to interview so that your margin of error is no more than, say, 2%. So for that, you use one of these formulas. First of all, if the value of P, which is the population proportion, is known to be roughly in the neighborhood of a value P star, then N, the minimum sample size needed to get a given margin of error, is given by this formula right here. So P star times 1 minus P star, and then multiply that by the square of Z sub alpha over 2, which remember is determined by your confidence level, divided by D, which is the desired margin of error. Okay. Now, if you have no idea what the population proportion is, then sorry, I just noticed this little thing with the notation. So PQ is the same as this thing right here. Remember that Q is just 1 minus P. So this is kind of an interesting intermediate algebra problem. The largest that this P times 1 minus P can possibly be is 1/4. That happens when P is 0.5. Okay, so if you have no idea what P is, then you can replace P star times 1 minus P star with 1/4. Okay, remember this is sort of a worst case scenario, so you're looking for the minimum sample size needed to guarantee that you get this desired margin of error. Okay, so it may turn out that you didn't really need a sample this large, but this will definitely work. All right, so we have an example of using that. All right, a public health survey is designed to estimate the proportion P of a population having defective vision. How many persons should be examined if the public health commissioner wants to be 98% certain that the error of estimation is below 0.05? When, and there are two scenarios. First one is there is no knowledge about the value of P. And then the second scenario is P is known to be about 0.3. Okay, so here's how we do that. First of all, for 98% confidence, I think we just recently did an example of a 98% confidence interval. Z sub alpha over 2 is 2.326. I believe that value is in one of those little tables that you have showing you the different values of Z sub alpha over 2 for different confidence levels. And the way that you get this is the Z-score that cuts off, if you're doing 98% confidence, it would cut off the outer 2%. So 1% on top, 1% on the bottom, okay? And remember, if you want to read that from the left side of the normal curve, you don't include the negative sign, okay? So this would actually be the Z-score that cuts off the top 1%, because we're trying to cut off 1% on top, 1% on the bottom. And then we want the error to be less than 0.05, so that's going to be D. You put that all into the formula. Use the second one that we just talked about on the last slide. N is equal to 1/4 times the square of Z sub alpha over 2 divided by D. So I plug in those two values, and that expression works out to be about 541.03. And remember, so what that means is the minimum sample size you need is 541.03 people. And you can't get 541.03 people. So if you need at least that many people, it really means you need at least 542. So minimum sample size problems, you always, always, always round up. Okay. So that is the absolute worst case scenario. You don't know anything about P. So what if P is known to be about 0.3? Can you get away with a smaller sample? Well, yes. So in that case, you use this formula. P star is going to be 0.3. So of course, 1 minus P star is going to be 0.7. The other part of the formula is the same. That works out to be about 454.46. You round that up to 455. So you don't need quite as large a sample. It's still a pretty decent sized sample though. Okay. All right, so the next example is doing a hypothesis test about P. So this one says a 5-year-old census recorded that 20% of the families in a large community live below the poverty level. To determine if this percentage has changed, a random sample of 400 families is studied and 70 are found to be living below the poverty level. Does this finding indicate that the current percentage of families earning incomes below the poverty level has changed from where it was 5 years ago? And as usual, they're giving me the value of alpha. Okay. All right, so I'm going to go through the list of 5 steps that we've seen on a previous slide. The first of those 5 steps is to write the null and alternative hypotheses. Now remember, on the last slide, it said we were trying to determine if that percentage had changed. So that is a two-tail test. The alternative hypothesis is going to be that P has changed. It is no longer equal to 0.2, which means the null hypothesis has to be that it equals 0.2. The second step is to identify your test statistic. And again, on a previous slide, I had this formula, you know, which kind of has the same form as other z-score formulas we've talked about. So this is in the sampling distribution for P. So that has a bunch of sample proportions. So an individual score is a P hat. Remember, that means sample proportion. Sorry, I'm just turning on a spotlight here so I can point at things. That's better. Minus the population proportion in this case, which is the mean of that sampling distribution. And then we divide by the standard error, which is the standard deviation of the sampling distribution. And that's given by the square root of P times Q divided by N. And it is a two-tailed test because in the alternative hypothesis, you have not equals, right? Okay. Step 3 is to determine the rejection region. Since alpha is equal to 0.05, which has come up several times before, that means our rejection region is z is less than or equal negative 1.96 or z is greater than or equal 1.96, and I found a picture of that. Okay. Oh, this is from one of your earlier slides. All right, I thought I recognized that picture. All right, so the next step is to calculate the test statistic. So remember, they interviewed 400 families, found that 70 of them were living below the poverty level. So that means P hat, the sample proportion, is 70 over 400, which comes out to 0.175. So our calculated test statistic is going to be, again, this thing. And when you plug in all those numbers, that comes out to negative 1.25. And you shouldn't take my word for it. You should be checking this on your calculator. Remember, we've talked in class about how these formulas can be tricky to put into the calculator. So just make sure that you're able to put that in and get the same value. Okay. Since, sorry, that is a typo. Excuse me while I fix that super quick. Since z equals negative 1.25 is not in the rejection region, and you can see that right here. I actually found this picture on Google Images, and that is also missing the negative. That is so weird. They made the same mistake I did. Okay. Yeah, I found this picture on Google Images with the exact correct z-score there. Same as the one from our problem. All right, so you can see that that z-score is not in the rejection region. The rejection region is less than or equal negative 1.96 or greater than or equal 1.96. So since that's not in the rejection region, we fail to reject the null hypothesis, which means, and remember, I want you to write something like this, an actual interpretation of what it means to reject or fail to reject. There is not sufficient evidence to conclude that the percentage of families earning incomes below the poverty level has changed. And then they suggest also calculating the p-value just for extra support for that conclusion. All right, so the p-value is going to be 2 times 0.1056, which comes out to 0.2112. Let me just show you how I got that. So this is a picture of the proportion of the normal curve that lies either to the left of negative 1.25. Oops, sorry, I'm not used to writing with this mouse. 0.25, or to the right of 1.25. So when you do a two-tail test, your p-value has to come from both sides. Remember what the p-value is. It's the probability that if the null, assuming the null hypothesis is true, what is the probability that you would get a sample as extreme as the one you got? So I wouldn't have cared whether my sample had been below or above the one in the null hypothesis. All right, so now I think you can see how to get that value, right? You just look up negative 1.25 in your table. The area to the left of negative 1.25 is 0.1056. You multiply that by 2 to get the entire region like what you see in the picture. And what that p-value means is that when the true population proportion is 0.20, you will get samples that extreme about 21% of the time. So that's going to happen like 1 time out of every 5. That is not at all unusual. It's definitely not strong enough evidence that the population proportion has changed. Okay, so that backs up our conclusion that we should not reject the null hypothesis.